Welcome. In this video, we'll be proving a cornerstone of mathematical analysis. It's known as Minkowski's inequality. By the end of this lesson, you will be able to prove Minkowski's inequality and understand its profound geometric and functional analysis implications. At its heart, Minkowski's inequality is a generalization of the familiar triangle inequality. Remember the triangle inequality? It states that for any two vectors, say u and v, the length of their sum is never more than the sum of their individual lengths. This inequality has a very clear geometric interpretation. The shortest distance between 2 points is a straight line, and it's always shorter than any path that goes from the origin to u, and then from u to the sum u plus v. Minkowski's inequality takes this idea and extends it to an arbitrary p-norm. It states that for any number p greater than or equal to 1, and for any two sequences of numbers x and y, the p-norm of their sum is less than or equal to the sum of their p-norms. In other words, the length of the vector formed by adding x and y component by component, when measured with the p-norm, is still at most the sum of the p-norm lengths of x and y themselves. It maintains that fundamental triangular relationship. This might look complicated, but we'll break it down step by step. Before we dive into the main proof, we need a couple of essential tools. We'll start with a classic inequality that will do most of the heavy lifting. This is known as Holder's inequality. It will be our key to unlocking Minkowski's inequality. It states that the sum of the absolute values of the products xi times yii is less than or equal to the product of two p-norms, where p and q are a special pair of numbers. Those numbers, p and q, are called conjugate exponents. They are any real numbers strictly greater than 1, with the property that 1 over p plus 1 over q equals 1. For example, if p is 2, q must also be 2. The formal statement of Holder's inequality is this. The sum of the absolute values of the product xi yii is bounded by the product of the p-norm of x and the q-norm of y, where p and q are conjugate exponents. In essence, this inequality tells us that we can separate the p-norm of x from the q-norm of y. It creates a powerful link between different p-norms. We'll take this as given for this proof. There's also a special case of Minkowski's inequality that is useful to cover. The cases for p equals 1 and for p equals infinity, called the max norm, are straightforward. For p equals 1, the inequality becomes the standard triangle inequality for sequences, which we know is true from basic properties of absolute values. For p equals infinity, which is the maximum absolute value among the components, the inequality also holds because the maximum of a sum is always less than or equal to the sum of the maximums. So, the infinity norm of x plus y is less than or equal to the infinity norm of x plus the infinity norm of y. Now that we have our main tool and have covered these special cases, we are ready to tackle the proof for the general case where p is greater than 1. It's time to build the foundation of our proof. Our strategy will be to work from the inside out, starting with the pth power of the sum. Let's focus on the expression for the p-norm of x plus y, raised to the power of p. This removes the pth root and simplifies our initial calculation. So, we'll begin our proof by expanding this sum of the pth powers of the absolute values of the sums. The first step is to use a fundamental property of absolute values. The absolute value of a sum is less than or equal to the sum of the absolute values. This is the simple triangle inequality for real numbers. Applying this, we can say that the sum we're interested in is less than or equal to the sum of the pth powers of the sum of the absolute values of xi and yi. Now, we'll perform a clever factorization within the sum. We will split one of the terms of the expression, vertical bar x underscore I, vertical bar plus vertical bar y underscore I, vertical bar circumflex p. Let's rewrite each term in the sum. We can take one factor of vertical bar x underscore I, vertical bar plus vertical bar y underscore I vertical bar, and pull it out, leaving us with vertical bar x underscore I vertical bar plus yii, p minus 1. Why do this? Because it allows us to distribute the first factor, which will create two new sums. Each of these new sums is perfectly structured for us to apply Holder's inequality. Distributing the vertical bar x underscore I, vertical bar plus vertical bar y underscore I vertical bar term, we get two distinct sums. The sum of xi times the other term, and the sum of yi times the other term. This is a crucial decomposition. Now look closely at each of these new sums. Notice their structure. They are both sums of products. This is exactly what Holder's inequality is designed for. In the next step, we will apply it to each of these. Our proof now hinges on applying Holder's inequality to those two sums we just created. Let's start with the first one. We'll focus on the sum of vertical bar x underscore I vertical bar times vertical bar x underscore I vertical bar plus yi p minus 1. To apply Holder's, we need to identify the two sequences being multiplied. The first is simply the sequence of absolute values xi. The second is the sequence where each term is vertical bar x underscore I vertical bar plus yi per minus 1. So, we set our A sequence to be vertical bar x underscore I vertical bar and our B sequence to be vertical bar x underscore I vertical bar plus yii. We also need to choose the correct conjugate exponents, p and q. We already have a p in our expression, so let's stick with that p. We'll use our original p and its conjugate exponent q, which satisfies the relationship 1 over p plus 1 over q equals 1. Now, let's apply the inequality to the p norm of A and the q norm of B. The Pn norm of our A sequence is the sum of xi part p, all raised to the power of 1p. This is exactly the p norm of x. For the B sequence, we need its q norm. This means we sum the qth powers of each term and take the qth root. The key observation here is that p1 times q is exactly equal to p. This is because, from 1 over p plus 1 over q equals 1, we get q equals p. Because p1, q equals p, the expression simplifies. We get the sum of vertical bar x underscore I vertical bar plus vertical bar y underscore I vertical bar circumflex p, all raised to the power of 1q. This is almost the p norm of x plus y, except it's raised to the power of 1q instead of 1p. Putting this all together with Holder's inequality, we find that the first sum is less than or equal to the p norm of x times this expression involving the pth power of vertical bar x underscore I vertical bar plus vertical bar y underscore I vertical bar, all to the power of 1oq. We can combine these two sums because they have the same qth root term. We can write this more compactly as vertical bar x vertical bar underscore p times vertical bar x plus y vertical bar underscore p raised to the power of p slash q. And crucially, by symmetry, we can do the exact same thing for the second sum. It will be bounded by the p norm of y times the same term, vertical bar x plus y vertical bar underscore p to the power of p slash q. These two results are the final pieces of the puzzle. Now we can assemble them. We have arrived at the climax of our proof. We have all the pieces, and now we'll put them together to reveal Minkowski's inequality. Let's combine our results. We started with the inequality that the pth power of the p norm of x plus y is less than or equal to the sum of two terms. We then used Holder's inequality to find an upper bound for each of these two sums. Now, let's substitute those bounds back into our main inequality. Notice the term that is common to both new expressions on the right-hand side. It's the p norm of x plus y raised to the power of pq. Let's factor that common term out. This gives us the p norm of x plus y to the p is less than or equal to the product of the p norm of x plus the p norm of y and the p norm of x plus y to the pq. Now we have the p norm of x plus y on both sides of the inequality. This is the key. To isolate it on the left, we can divide both sides by the term on the right, assuming the term is not 0. So we get the pth power divided by the pq power. Remember, when you divide powers with the same base, you subtract the exponents. The exponent on the left becomes p minus pq. If we get a common denominator, this is p times q minus p, all over q. Factoring out p, we get p times q minus 1 over q. Here's the magic. We defined q by the relationship 1 over p plus 1 over q equals 1. This means 1 minus 1 over q is equal to 1 over p. So the exponent simplifies to p times 1 over p, which is just 1. This means after dividing, the left side is simply the p norm of x plus y, and the right side is the sum of the p norm of x and the p norm of y. And with that, we have proven Minkowski's inequality. we have shown that the p-norm is a valid norm and that it satisfies the triangle inequality for any p greater than or equal to 1. So what did we just accomplish? We proved that for any p greater than or equal to 1, the p-norm defines a distance that satisfies the triangle inequality. The fact that Minkowski's inequality holds means that the function x per xp is indeed a true norm, or a way to measure length in a vector space. This has profound consequences across many fields of mathematics. In geometry, Minkowski's inequality tells us that the shortest path between 2 points in any p-norm is a straight line. It ensures that the space we're working in has a sensible geometry. In analysis, it is essential for defining the LP spaces, which are fundamental in the study of integration, Fourier analysis, and functional analysis. These spaces are complete metric spaces, meaning sequences that get closer and closer to each other always have a limit within the space, which is critical for defining things like integrals and derivatives. For example, when solving differential equations, solutions often reside in these LP spaces. Proving that these spaces have a valid norm allows us to define convergence and ensure that our solutions are well behaved. In summary, we started with a simple geometric idea, the triangle inequality, and used the powerful tool of Holder's inequality to generalize it. This result, Minkowski's inequality, is not just an abstract theorem, it's a foundational result that underpins our understanding of space, distance, and functions across the landscape of modern mathematics.